So to introduce this topic, it is hypothesized that zonally asymmetric thermal forcings, which is the idea of land-ocean heating contrasts, is a primary driver of planetary geostrophic motion. And under global warming, in this case Arctic amplification, the rapid warming of the Arctic relative to the equator causes a weakening of the meridional temperature gradient, subsequently reducing the mean zonal wind speed. So the study that we looked at examines how weakening this wind alters the atmospheric dynamics, specifically the transition where the atmospheric response to surface heating shifts from being confined near the surface to propagating vertically throughout the troposphere. And this deep vertical propagation is theorized to significantly increase the amplitude of planetary waves, resulting in a wavier jet stream. And this is important to understand as this dynamical shift is critical, as these jet stream waviness meanderings can be a mechanism for driving persistent extreme weather events. The methodology in this particular paper contrasts greatly with other studies regarding jet stream waviness. Other studies focus more so on quasi-geostrophic forcings, which in turn cause amplification of the jet stream waviness. So to test this idea proposed by the paper on the planetary scale, we solved the governing linearized planetary geostrophic equation regarding the fundamental process of heat transport across the atmosphere vertically. And then we compare the strong wind regime to a weak wind regime and observe the changes in wave propagation as a result.
So, like Scene already outlined, the goal here is to study how temperature can cause perturbations of pressure in the atmosphere, and then how this can have broad effects on large-scale atmospheric phenomena like these jet streams or eddy currents. So the equations that we're working with here essentially all just come down to this last equation 7, and the idea is we want to derive some relationship between the z derivative, so the height derivative in the troposphere, of our pressure perturbation with respect to the thermal forcing that we're considering. So we start off with these first three terms, this equation set 1. These are just derivatives of a pressure field in the atmosphere with respect to y, x, and z. So that's the longitudinal, latitudinal, and height derivatives, respectively. And then we're going to apply two equations that are well known in the literature already. This first one is the Sverdrup relationship, which relates the density, the z velocity, the x velocity, and this rate of change of the Coriolis parameter all together. So it relates, how our pressure field is changing with respect to x and z to quantities like, how the Coriolis effect changes as we move along our x. Okay, and then the second equation we want to use is this equation number 3 here, and this is the heat transport equation. So this takes some theta L, which is a potential temperature in the atmosphere, and it relates it to these pressure derivatives as well as some thermal forcing term. And it was shown in Moon and Cho, which is a paper we've put in our references, that essentially these are all you need to care about if you care about the leading order terms of this geostrophic motion that we're considering. So from these, what we do is we're going to begin by writing our pressure field PL as some average pressure, PSL, plus some perturbation phi. So PSL here is some pressure that is driven or drives, depending on your perspective, some wind, U, some mean barotropic wind, U. So this is like an average pressure. And then we consider this average pressure plus some small perturbation that's, very, very small relative to this mean pressure. Okay, and this pressure perturbation is going to be generated by QL. Then we can use some linearized steady-state geostrophic equations that are demonstrated in Moon and Cho to write down the following relationships. The first relationship tells us how the wind, this x and z derivative of our perturbation, and the z derivative of our pressure field is related to this change in forcing, or this forcing constant, this thermal forcing. And the second equation is really just this Sverdrup relationship again. So now we get to relate the x derivative of our perturbation to the z derivative and some scaling constant here of the z change in pressure. Okay. And with both of these in hand, we can go ahead and combine the two into this equation 6, which kind of relates all the things we care about so far into one big model. So this relates our change in Coriolis parameter, which is our beta. It relates our phi, or perturbation. It relates this QL, which is our our thermal forcing. And then we really only care about phi as it changes with respect to height. So we'll do this thing called zonal integration, which is integrating with respect to x, I think, to find this final equation, equation 7, which is the equation we'll be studying, and it relates this perturbation and some of its derivatives to this thermal forcing term on the right-hand side here. Okay. So with this in hand, we can actually begin to look at our numerical methods. So again, we want to study this equation 7 with these constants inside of it. And what we're going to do is we're going to apply 3 numerical methods. So first, we'll discretize it and then solve this system using a matrix inverse approach. And then we'll also implement numerically some of the analytic solutions provided by the authors. And then we'll also use a built-in solver black boxed through SciPy's solve BVP method. So the discrete solution is we just take our equation 7 here, which is this guy, and we'll use a center differencing to expand the second derivative and an upwind differencing to expand this first derivative. So these are just pretty standard differencing techniques. And then with all of this in hand, we can take the coefficients of each of our phi L of zi plus 1, zi minus 1, and write down a tridiagonal matrix whose entries are given by this equation right here. And with this in hand, we can write B for our forcing vector here, and we have a matrix inverse problem now. So now A phi L equals B, and so if we were to apply A inverse to the left on both sides, we would be able to solve for phi. And that's exactly what this first code block does. So, we have some constants here for our stepping. We have some linear spaced grids for our x and z inputs, and then our dz. And then this function just constructs this diagonal matrix using SciPy's sparse diagonal method, constructs our forcing vector, and then returns the solution, which is our phi L. But the paper also specifies some boundary conditions. The ones that we consider are Neumann conditions at the top of our z domain and the bottom, which is these tropopause and the surface respectively. And so this function is just the same thing. It constructs this tridiagonal matrix, and then it also modifies the matrix so that these Neumann conditions are accounted for, and modifies the forcing vector as well. And so what we do is we make some choice of our f function here, which is one of the functions that you kind of have control over in this equation 7. You can see right here we have this f function. So the authors choose this function sine 2x over 2. And all that this code block does is it just says, okay, well, for each value of x, let's solve the equation with that value of x, and then we'll add this to a big matrix that will give us the total evolution of phi with respect to x and z. And we do this for both a strong and weak wind, which I guess I should talk about for a second. What we should notice is that equation 7's characteristic polynomial, it's going to have different solutions. Sorry, equation 7 will have different solutions based on what the sign of its discriminant of the characteristic polynomial is. So if u is bigger than this constant mass here for h squared beta ls, then we'll have what's called the strong solution, and if it's smaller, then we'll have the weak solution. And so we compute both of these here, the strong wind, which is u equals 1.5, and the weak wind, which is u equals 0.5. Okay. And with these solves, we just do some simple calculations here, finding some maxima and minima, so we can have consistent plotting. So now we'll move to this analytic solution, which the authors provide. And again, they provide one for the strong wind and one for the weak wind. So these equations are just, they've done some pretty laborious calculations to solve for these. And we just implement them here in this analytic function that takes in an x, a z, a u, and a parameter weak. And if weak is 0, then we compute the strong wind. And if weak is 1, we compute the weak wind. And so that's all this function does. Then we do the same thing. So we create some array to hold our results. We iterate through for all choices of x, or in this case for f of x, and then we just store all these in a big matrix and plot them in a similar fashion. Then we also attempted to implement a pre-built solver using SciPy's solve BVP function. To do so, we're going to write equation 7 as a system of 2 first-order equations. So we'll write y equals d phi dz, and then y prime, which is the second partial with respect to z of phi, as this equation. So this is a pretty simple standard change of variables. And then we just construct this function that takes in an x and takes in a u and solves this boundary value problem using SciPy's IVP. So this method up here just constructs the system as a NumPy matrix or an array. We have some boundary condition function that keeps us in von Neumann conditions. And then we use this integrate solve BPP function.
As Connor suggested earlier, the numerical methods that we used here all use the same simulation, and this simulation is revolving around the wind threshold outlined in the paper, where the strong wind parameter is 1.5 and the weak wind parameter is 0.5. All the methods that we used to investigate this paper all showed signs of parallel findings to that of the research paper. Of the three, the discretization method, or method one, strongly mirrors that of the paper's findings, with the analytical and pre-built implementation contrasting slightly. But despite this, both of these also show trends congruent to that of the findings in the paper. So this is the figure for our method one, with the top half being the strong wind case and the bottom half being the weak wind case. The left shows the perturbation values, and the right shows the actual top of atmosphere pressure values. And this is the same format across all numerical method figures. So as you can see here, we can see, if I point to the perturbation at the top left, we can see that the magnitude across the figure is definitely weak, with the darkish green here being around 0. And we can also take note that there is a confinement here near the surface where there is a line of sorts that shows 0 perturbation. And we can see that there's some sort of a waviness pattern going on with going in and out with positive negative values, which is to be expected as seen in the actual paper findings. And then when looking at the weak perturbation values, we can see that this is the same pattern we see in the strong wind, but the magnitude is much greater. And this is to be expected given the findings in the paper as well. Now looking at the strong pressure values, we can see that there is some little waviness across the board. This is more so akin to what we would typically see in a jet stream on, say, like a weather map, a surface weather map. And then comparing that to the actual weak pressure values, we can see that there is a much greater amplitude of the waviness. And again, this is also to be expected when looking at the paper's findings. This further shows the idea that weak winds help waviness and meandering of the jet stream itself. Now we're looking at the actual analytical figures for the analytical method provided also by the paper. Starting off with the strong perturbation values, we can see that there is somewhat of a pattern similar to that of the previous method. We can see that this in and out type of waviness that we see here near the surface is similar to that of the confined surface for the discretization method. We also see some signs near the top of atmosphere where we can kind of see some sort of growing magnitude, which we would expect to see for the discretization method as well. But this seemingly looks like a more zoomed in version of the confined surface perturbations. Now looking at the weak perturbations, this is also the same pattern as we see in the strong perturbation, but it's flipped now. I'm not too sure how to analyze this in particular, but the one thing we can take away from this is that it's still mapped out the same perturbations that we see in the strong perturbation values as well as the discretized perturbation values as well, also seen with the same pattern as the surface. So we can get an idea that this still somewhat follows the same idea and trend that the other method has. Now moving to the strong pressure values, we see again this has the very straight, stable looking jet streams, slight waviness, which is to be expected, but still also congruent with that of the paper's findings. Now looking at the weak pressure values, we see that there is a very intense wave propagation here. But again, this still does follow the trend despite it being slightly intense in comparison to that of the paper and the previous method. But again, this still further shows the idea that the weaker winds do help increase meandering of the wave of the jet stream waves. As you can see, the penetration from the higher values from the surface upwards into the top of the atmosphere is still prevalent. And finally, we have the pre-built solver method, method 3. And again, this has similar discrepancies that we've seen in the previous method. But again, still shows that general trend that we were looking at in method 1. Both the strong perturbation and the weak perturbation show very similar graphs. But again, the pattern is still that similar to the one seen in the analytical solution, which is the similar pattern to that of the surface confined perturbations we expect to see in the paper as well as the method 1. Now looking at the strong pressure and the weak pressure values at the top of the atmosphere, we can see that both are very wavy, with the strong pressure being similar to that of the weak wind of the previous methods. However, if we compare both the strong pressure and the weak pressure, we can see that the weak pressure still has a higher amplitude compared to that of the strong pressure. We can see that these values are still penetrating deeper compared to the strong pressure value. And again, this is still the similar findings that we see in the other figures. However, it is not, of course, the same magnitude, but it still further shows a congruent finding to that of the paper and, of course, the rest of the methods. Now, with that being said, the models we explored here do support the hypothesis explored in the paper, and that would be the Arctic amplification can physically change the planetary wave propagation by causing them to meander more so. When winds become weak, the thermal forcing from the land-ocean contrast is able to vertically interact with the jet stream, which then in turn causes bending into high amplitude waves. The current model that we reflected in our study, as well as the paper itself, is that of a rigid lid, where the tropopause is set to a finite variable, in this case z equals 1. A more realistic approach would be the implementation of a radiating boundary condition, similar to an uncapped tropopause that the paper does go into in the later half of the paper. And this to accurately predict the idea of westward tilt. A future study could also include the usage of vertical wind shear to test how it would interact with the planetary waves as well.